I made this slide for a bigger project. It was only going to show up for a short time in that video. This is all bonus math. This isn't anything that's actually required for that video. But it's kind of nice, so I thought I'd go into some more detail here in case anyone wanted to hear the whole story. Start with the big stuff at the top. This is all about what's small and smaller and even smaller than that. This is calculus, so it's dx and dx squared and dx to the third. The most important thing to notice is that the input we're given doesn't have anything small. This is smaller than any of the numbers that normal people talk about. These are calculus numbers. The point of this video is to make a derivative of a function. But the problem is we're just doing an estimate, and we can't really get dx as small as we'd like. So we're trying to figure out how bad that hurts us if our estimate isn't that good. So the first thing we do, well, we already have f of x, and we're just assuming that we can turn it into a polynomial here. We're just going to take the Taylor expansion. If you haven't seen this before, we're just converting the function into the simplest math you can think of. Some number times some number squared plus some number times some number to the third power. Stuff you can do on a calculator by hand. And the nice thing about that, even though I don't know these exact values, I know they exist. So now I can apply that to x plus dx, which is required. This is basically the formula for a derivative, except taking a few liberties here. By making these polynomials, we can actually do the math and see what happens. We can multiply things out. We can say what is x plus dx squared. So this is really just to prove a point. We're not actually going to compute this. We're just showing that no matter what function existed, we can still do this, and we can still see just how many dx's are in each of the terms. The point of making this into a polynomial like this, we know how to do all of these operations. X plus dx squared, you could look that up. It was something you learned before algebra class. And if you follow that through, you're going to get some dx's, which, as we say, are smaller than anything you would consider in your input. And we're going to get some dx squared. Those are smaller, and, of course, dx to the third. We plug this answer, what is f of x plus dx, into here, and we also plug the initial function into here. And that's where we get this big long equation. Again, a lot of stuff. You wouldn't want to deal with this all the time, but there's nothing here you can't deal with. It's just finding similar things. C0 minus C0 disappears. So anyway, this gives us a look at what our good estimate's going to look like. And this is where we started. This was the good enough estimate, and the whole point of this project was to come up with a new and improved estimate. And well, part one, we do this good estimate again, but instead of looking at this dx that was small, we're going to look at 2dx. So it's still small, but it's not quite as small as our first estimate. And we go through this same process, and we get something very similar looking, just a few different constants. So now, what did I do? I wanted to get dx really small. I wanted to say f of x minus f of x divided by 0, but that wasn't going to work. So I just want dx to get as small as I can get it. Well, I have an estimate at 2dx. I have an estimate at dx. So if I want to know what's going to be at 0, all I have to do is extrapolate. I have 2 points and I want to know a third. And because the numbers are so simple, all it is 2 times this, what you get with x plus dx, minus this new one that we did here with dx being twice as big. And you do a little bit of math. Again, you're just plugging in some values. Here you're multiplying things by 2. Nothing you couldn't have done on your own if you had to. And anyway, you simplify that, and here is the answer that we get with our new improved estimate. So let's put all this back into context. This was the original good enough result. And notice these small things here. There's dx's and dx squareds. And then here's the new improved result. Very similar, except there's no dx term and a slightly different dx squared term. And then the correct result. This is what the derivative should look like. And that was another reason for taking this Taylor expansion. We could do the derivative of the function without actually knowing what it is. And you notice all 3 of these lines are very similar, but these 2 estimates have terms that aren't in the correct result. So I believe the technical term is these are the errors. This is the part that we want to go away. Now the good thing, this error, it's small. And that's why we call it good enough, and in a lot of cases it is good enough. In the previous video in this series, I actually showed you had to, even if you zoomed in a lot on the picture, you couldn't see the problem. You actually had to look at the numbers in the debug window because they were that small. And in calculus, you can actually get this, in calculus class, you can get this dx so small that you really don't care about it. And if you ignore the small and smaller errors, then the good enough result looks like the correct result. But the point of this exercise is I'm not in calculus class. Instead, I have to estimate this with a dx that's a floating point number, something the computer can handle. So it's going to be small. It's just not going to be as small as I'd like. So what happens? This new improved result, we got rid of the small error. There's still a smaller error, but it's going to be so much smaller that for my purposes it's perfect. And in fact, I think there's some numbers in the previous section of this video, and the next section of this video will show all this stuff graphically. All right, thank you for watching.